Hello and welcome to Introduction to Computational Fluid Dynamics, CFD. Today we'll be talking about very fluid fields and natural visualizations. I'm Professor Steve Miller. In the previous class, we talked about methods of investigations for problems. For example, experimental methods like in wind tunnels, theoretical methods such as in doing analysis with pen and paper, and of course the topic of this class, which is computational fluid dynamics numerical. We talked about the advantages and disadvantages of using these approaches in a combined setting and the advantages and disadvantages of that. We also talked about the impact of computational fluid dynamics in the aerospace industry. We also went over, which is critical to the class, the computational fluid dynamics process. Remember, this is the pre-process and problem definition, the solver, and the post-processing and analysis phase. In this class, we'll talk about different computational fluid dynamics codes, the differences between research-based codes and commercial codes. We'll also talk about serial versus parallel codes, that is, a code running on one processor versus multiple processors. There's a tremendous number and differences in the codes, and often you have to choose the right code for the right job, just like you would choose the right tool for the right job. We'll also talk about flow visualizations, and this is a lot of fun because we'll look at different flow fields and their meaning. And then finally, we'll compare the natural visualizations of flows you might see appearing on aircraft when you're out at an air show or airport, or just watching an aircraft fly by perhaps, or see online or in movies, and see how they compare with computational fluid dynamics. Now, there's many different types of computational fluid dynamics codes, and it's often the case that you have to choose the right one for the right job. There are a few jack of all trades and masters of none, if you will. If you're a user, then you obviously need to select the best code for the problem that you're trying to solve. Remember, the most important part of the process is just defining the problem. And once you do that, and if you're aware and have access to different kinds of codes, you'll be able to apply a particular code to that particular case. Often when you're learning CFD, you might have access to one code like Fluent or Star, or in this class, we're using a set of open source codes to learn to obviously keep costs down for students around the world. There's other factors that might affect your choices. For example, what kind of computer hardware do I have? So even if you define the problem and understand you want to do a time-dependent solution, you may not have the computational power to do that case, so you might have to do a steady case. So you have to understand what kind of hardware you're going to run the code on. How many processors do you have? How much memory do you have? These are important factors. Also, if you have that computer, say you have access to a large cluster or maybe a desktop computer and you need to use it for other things like email and work or other classes, you have to understand how much available computer time you have. You may not have hundreds of wall clock hours on your personal laptop when you have to use it for many other things in your life. If you're on a cluster, you might be allocated only, 10,000 hours a year, and it's very easy to use up 10,000 wall clock hours a year on a high performance computer. This all translates to finances and money. Wall clock hours, CPUs, computer time, hard drive space, money, and your time as an engineer is valuable. And all these things can be quantified in dollar amounts, especially if you're in a finance group in an aerospace organization. Most importantly, it takes your time. So some codes are going to be more time intensive for a user versus other codes. A lot of the commercial codes try and automate and give you default options for everything that you need. In a research environment, often you might be programming on the code and changing it and recompiling it and validating it before you even go to a production run. This might take a tremendous amount of user time. Grid generation is where most users in CFD spend most of your time, and you should expect that's where you'll spend most of your time too if you're doing computational fluid dynamics through the whole process. In the end, what is important is the kind of a result you're trying to achieve. Are you just trying to find drag, or maybe you're trying to do something more complicated and find turbulence statistics from a DNS simulation? These are all choices that you're going to have to understand and make through the computational fluid dynamics process. We divide CFD codes into research-based codes and commercial codes. Research-based codes might be ones developed by, say, universities or governments or industry, where they're created for studying CFD and, of course, doing CFD itself. The second class of codes, commercial codes, are ones that fall into the category of being sold by companies to other companies with license use. So another way to look at it might be that research codes are often free to the user because they're for research and created by researchers for researchers, or sometimes used in production. And commercial codes are really created for the purpose of the business and financing their company. So a few points about each one. Commercial codes, the source code is almost always restricted. Source code is the code that is used to compile the solver or grid generation or any other step of CFD, and it's usually restricted. It's going to be under a software patent, and unfortunately the user can't ever see it. So this means as a CFD practitioner, you can never go into the source code and actually see the equations which are programmed in the code. Obviously, companies do this so they can make profits by providing services and licenses. Sometimes CFD codes per user can cost up to $10,000 per year and up. So it is very expensive sometimes to use a commercial code. A lot of the commercial codes, for example, like Fluent or Star, offer student versions for nearly free or very low cost. The idea is that they let students use their versions, and then when they go through a company after they graduate, then they'll say, hey, supervisor, I know Star or I know Fluent and I can use that. So commercial codes, of course, cost money, but they're really generally unrestricted in what you can do with them. These are almost always created by industry, that is, companies like Fluent, for example, ANSYS and Siemens. And there's even smaller companies that create very specialized software for CFD to approach maybe particular problems. Turbines are very popular. There's lots of, as an example, very specialized turbine CFD codes. There's also companies that create just visualization software and just grid generation software. And I've used these types of software from commercial vendors, and they are really excellent and they have amazing user support. For example, one of my favorite grid generation software is Pointwise. And Pointwise, unfortunately, costs a lot of money a year per license, but it makes really high quality computational grids. For visualization, I've always been a fan of TechPlot. That's also another example of commercial software for the purpose of visualization. And the other set of codes, some points to take away might be that if it's a research code, not always, but a lot of times, the source code might be available to the user. And the user can use the compiled version and just perform the CFD calculations, or they can recompile it for their own computers, or they might even be able to go in and change the source code and inspect it and look for bugs. So this gives tremendous power to the user because they have one of the freedoms that is important for users of computers. They have the right to see the source code that's running on their computer. Typically, research-based codes are created by nonprofits like universities or sometimes government agencies like NASA as one of many examples. And they're supported, for example, at universities by grants, or if it's an open source project available online, by volunteers. The code we're using in this class is an open source code created by a consortium of universities. Often these codes are free and not typically restricted by nationality or organization. That is to say, however, that some research codes coming from, say, NASA or another government organization in the United States may only be restricted to United States citizens or people with security clearances. This is especially true for research codes involving hypersonic high-speed flows. So research codes are created by industry, governments, and academics. Commercial codes are typically created by small businesses or large industries like Siemens or ANSYS. Now, either class of this code, research code or commercial code, can almost always be run in serial or parallel. That being said, if it's a graduate student creating their own code for the first time, or generally when CFD codes are created for the first time, they're running in serial. By serial, I mean it's a code running on a single processor. It has one process in the computer. If it's running in parallel, then it has more than one. It might have two or more processes. The advantages and disadvantages are something we'll talk about now. So in serial codes, all the computer instructions are run in serial by one processor. It is much simpler to create these types of codes. Because it's just like writing a regular program. You don't have to worry about all these other types of commands in the source code that involve with like parallelization and communication. We'll talk more about those details in the parallelization section of the class. Parallel codes mean that there are multiple sets of the instructions of the source code running on different processors at the same time. However, they're just working on different parts of the problem. This can be illustrated in the upper right figure. So if the problem is represented by this first column here, we can divide it into 4 parts. There are corresponding instructions, which are in these 4 rows for 4 processors for a single problem, running simultaneously. And these are given to 4 different processors, for example. If I'm using 10,000 processors, which wouldn't be strange at all in today's age on a supercomputer, then I would of course have 10,000 processes. Down here in the lower right corner, you can see the division of a typical CPU. CPUs today typically have cores. This particular CPU has 4 different cores. You can see that the problem instructions all go to these 4 different cores individually. So the advantage of this is that it takes advantage of modern computer architecture. Almost all good CFD codes can run in parallel now. In this class, we'll mostly be focusing on serial codes. Not everybody has access to a multi-core processor, let alone a cluster, to really take advantage of the parallelization. Also, there's extra complexity when operating parallel codes that maybe isn't the best to exercise when you're first learning CFD. But near the end of the class, we'll talk about the outcome of these, and we'll show a few examples now. Typically, at the end of a CFD calculations, both approaches should create the same result. That means at the end of a parallel run, all the processors take their result and combine them into a single result, which should be equivalent to the serial process result. Now, there's many different types of parallel processes happening in a parallel CFD run. Let's just look at some of those so you understand the big picture. First of all, remember parallel means across computers. That it could be called multiple computers that are connected by Ethernet. It could be on some kind of high-speed communication network, and it could just be on a single desktop computer having multiple cores. For example, at the time of this creation of the video, 64-core processors are starting to hit the consumer market. So I have some friends in the math department, and in their offices, they've built 32 and 64 core computers. In my research group, we have access to the university cluster system, which uses tens of thousands of cores in a run. This is totally common in university environments today. At large government organizations, they could have even more processor power. Parallelization can also happen on a single computer, as I just mentioned. The work is divided, ideally for a computational fluid dynamics run, evenly across processors. So if you have a problem and there's 10,000 grid points and you have 10 processors, ideally you would want to put 1,000 grid points on each processor and have the processors communicate to each other about the work. This is really a great parallelization study if the code can be easily parallelized. We'll talk about some of these things later too. There are very specialized algorithms to divide these problems automatically by the grid, or maybe it's a linear algebra problem by the order of the matrix and selecting multiple divisions of rows and giving these to different processors. Another type of parallelization, which is used less commonly in CFD, is the master worker approach, because it's a tiny bit less efficient, but it might be more efficient for other parallelization problems. This is where a single processor, the master processor, if you will, reads the problem and understands it and distributes the work to all the workers. This has more traditional names in the community, but many people say master worker today. All other processors are doing all the work. For example, in a factory, perhaps, there's a foreman, and the foreman tells 20 workers all have different tasks or the same task and different parameters. And at the end of the day, they all come back to the master and they give the master their completed work, and the master collects all the values and put them together and gives it back to the boss, if you will, which is the user, you. There's two major types of memory architectures in this parallel process part of CFD. There's shared memory and distributed memory. So if you're sitting at your desktop watching this, you might have a CPU with multiple cores. Well, all these cores can access the same memory addresses. This is shared memory. So older Cray supercomputers were shared memory machines. They might have hundreds of processors, and they can all share and examine the same memory bank. These computers were extremely expensive, and they still make shared memory supercomputers today, but they're much more rare. Distributed memory machines are much more common. This is where the memory is distributed across CPUs. For example, CPU 1 can access memory bank 1, and CPU 2 can access memory bank 2. But CPU 1 cannot directly access memory bank 2, and CPU 2 cannot directly access memory bank 1. So how do they access each other's memory when they need it? Well, in CFD, they may not, or they may only need a very select portion of the other CPU's memory. We'll talk about this parallelization strategy later. It turns out in general, CFD problems can be easily parallelized because generally CPU 1, 2, 3, etc. only need access to their particular part of the memory. And as the solver progresses, as it's solving the problem in time or in time invariant problem, they do communicate. And so through the Ethernet, the CPU might read its own memory and send it through an Ethernet cable to another computer where it receives it and has access to it. But in this case, CPU 2 has to tell CPU 1 that it needs that particular memory. As you can see, it gets very complicated to write these kinds of codes because you'll have to ascertain in advance that CPU 2 might need CPU 1's memory. And so CPU 2 would have to tell CPU 1 it needs its memory. But how does it know that? So there has to be some very logical process in the programming of these large-scale parallel solvers for CFD. Sometimes parallelizing the CFD code itself from a serial code to a parallel code can take easily months, if not almost as long as actually creating the original CFD code itself. Today, there's a new rise of graphics processor unit computing, GPU computing. I'm sure you've heard it in the news. There's lots of GPU-type companies that have come up, and they, of course, were originally created for computer graphics, but now they're using the processors on the GPU card to accelerate CFD solvers. Some CFD can actually, the solver at least, be completely performed on the GPU itself. This is a little bit more rare, but I'm seeing codes emerge that do that. There is debate in the community, the research community, about which approach is better. A purely traditional approach running on the computer CPUs without GPUs, approaches that make heavy use on the GPUs, or some combination of the two. It's very likely that hybrid approaches are going to emerge as the successful winner here, because there's certain parts of the C problem that work better on the CPU, and certain parts of the problem that work better on the GPU. So why not use both to our advantage? So there's a large number of CFD codes available, and this is an incomplete list, which I took a screenshot from Wikipedia of just available CFD codes. This is a list of simple open source ones. For example, here's the second page of the incomplete list of CFD codes which are open source. So you can see on Wikipedia they try to make a list and give you links. One example might be the SU2 code that came out originally from Stanford, is now being written as in a university consortium. So there's lots of choices. Another choice here, which is extremely popular, is OpenFOAM. This is an open source free CFD solver, but it was originally written just to evaluate numerically just general partial differential equations. So how do you know what all these do? Well, you have to go and read about them and understand them, and maybe one particular code is really great for the particular problem you're solving. There's also a list of commercial codes, and this list isn't exhaustive either. Today there's even many more. In this class, we used to use the star CCM solver. That's why there's an arrow here. It's just star CCM plus right there. And that's developed by the Siemens Corporation. In fact, they have offices right in Orlando, Florida, right down the road from us. Another very popular commercial code is Fluent, and I also have a student version. So if you want to take the time to look at one commercial code and a student version, which should be completely free to the student as the time of this video is made, try out their webpage, look at their code, and it'll contain everything from grid generation to the solver to post-processing. You can read in CAD and try things out. The student version is basically free because they limit the number of grid points that you can have in your solver to something like, I don't know, 10,000, which is a reasonable amount for a student solver on a personal laptop. This is quite confusing and overwhelming to people because there are so many codes that it's impossible to understand them all. And many people really only understand one or two or maybe even three at a very deep level if they're a practitioner of computational fluid dynamics. What's thankful to us is that they generally use all the same process, and you'll have to try and pick the CFD solver that is right for your problem, which I hope that you carefully defined. Let's look at one example from one of these solvers. We won't be using this solver the rest of the class. I just want to illustrate it with SOD's basic shock tube problem. So this comes to the PET-C example, which you can download, and it is open source for a particular shock tube problem. Remember, a shock tube is where you basically have a pipe and you have set up a pressure system to create a shock wave that propagates down the tube. It's worth looking up in your compressible flow books if you haven't looked at this in a while. Basically, PET-C is a series of libraries that are pre-written in a parallel framework, and it uses the basic linear algebra system and linear algebra pack. These are basically linear algebra solvers that can help that are called, and they're called by many different codes. They're just standard libraries. If you use MATLAB, you're essentially using BLAS and LAPACK, and you probably never even knew it. It also has a message passing interface, MPI, which is probably one of, if not the most popular libraries for communicating data between processors. So this is a library in Fortran or C typically that a solver written in any language really can call as a library to send data across the network. And it can also work on a single computer, so you don't need to use it on a high performance computer. It can also work on your desktop you're watching this video with. It has vector and matrix creation and all kinds of other utilities. But it's really great for just trying out some simple things here. And we're going to try out a SOD shock tube problem. Let's look at an example of just a serial versus parallel code. So we'll look at SOD shock tube problem, as I mentioned. In the lower right here is the typical domain. So here's the boundaries. And then there'll be a left area and right area. In the left area, I'm going to have these properties of density, pressure, and velocity. And in the right, I'll have these properties of density, pressure, and velocity. So you can see on the left, I have a pressure, for example, of normalized 1.0. And on the right, I have a pressure of normalized 0.1. The density is also fractional. And there's an initial velocity in the right field. So what's going to happen is they're in a real shock tube, they actually have like a little metal plate which they burst to let the shock form, and it'll go from left to right in the problem. That is, it goes from a region of high pressure to low pressure. So there are analytical solutions for this particular problem, and we'll be looking at those in the case. Oh, I forgot to mention boundary conditions. So the boundary conditions on this darker blue color are just a solid wall. This light blue line just represents the discrete change in the densities, pressures, and velocities of the fluid. So we're going to look at what happens when we solve this. We're going to model this flow with the Euler equations, which are basically the equations of motion. It's going to be conservation of mass, momentum, energy, and a gas law, but the viscosity is zero. So it's an inviscid fluid. So this is a very typical run with an analytical solution. And we're going to compare our numerical results with ones evaluated with MATLAB. You can find Gary Sod's original paper at this following link. So let's look at the solution at one particular time using PET-C. This is a plot of density. On the y-axis, we have normalized density from 0.1 to 1. On the x-axis, we have the length of the tube from 0 to 1 normalized. On the previous page, you can imagine that where my cursor is now, this is the value of x equals 0, and this is the value of x equals 1. Now, we've evaluated these equations of motion with these boundary conditions and initial condition with both MATLAB and PET-C, just as a comparison. Usually we would compare them with an analytical solution. You can see that the serial, that is single processor MATLAB solution, follows the line with little x's. The PET-C result obtained solution is the light blue line. They're in fairly good agreement, except in this region of near x equals 0.4. For now, we're not going to worry about the residual or the error or independent studies. We're just going to focus on some basic parallelization. So this idea is we have two different solvers, one written in MATLAB and one written in PET-C, and they're in relatively good numerical agreement. So for now, we won't be too skeptical, and we'll just keep going. You might ask now, what happens if I add another processor? I go from a serial run to a parallel run. That is, I increase the number of processors from 1 to 2. Well, let's look at one type of study. In the graph, on the left, we have computational time versus number of CPUs on a grid size of 100. The grid size of 100 remains the same irrespective of the number of processors we're using. So there's 100 grid points from x equals 0 to x equals 1. The y-axis of the graph represents the time in seconds, and the x-axis represents the number of CPUs. The time in seconds is the amount of time that the processor used. It is not wall clock time in this case, so it's consistent. If you run the same program over and over on your laptop, for example, you might find there's different wall clock times. Why is that? Because there's other processes on your computer. For example, you might run it once and there's no other process happening and you get a wall clock time of 1 hour, and you might run your program again with all the same settings, except maybe your processor is doing something else because you're surfing the internet or it's downloading an update from Microsoft or Apple. And it would take 1.2 hours. So you can't necessarily compare directly the actual time from the actual clock on your wall. You have to look at the amount of CPU time that was spent on the problem, because that should be consistent. And that's what we're doing here. Now, for this particular problem of 100 grid points with the Euler equations, with these boundary conditions, it took the time of 0.2 seconds on one processor. So the x-axis for both these graphs is the number of processors from 1, 2, 3, 4, 5, 6, 7, 8. So from one processor, we took about 0.2 seconds, and to two processors, this is not a 0, and here, this is 0.1 seconds. So you can see for the PET-C code from one processor to two processor, we've decreased the amount of time spent on the problem by a factor of about 2. That's wonderful. And you can see that in the computational speed up versus number of CPUs for the same grid size in the right plot. We went from a normalized speed up factor of 1 to 0.5 from going from 1 to 2 processors. So you can see there's two ways to plot this type of data. And there's all kinds of ways to plot parallelization studies. Now you might think, wow, ideally if I went from one processor to two processors and I found the problem in half the time. If I went to 4 processors, I might, again, half the amount of time. Now, let's look at the left graph. I go from 2 processors to 4 processors, and it looks like I've only got a time decrease of a 0.01 from 0.1. That is, we're about 0.1 to maybe, I don't know, 0.85. It's not down to 0.5. You can see that over here in this plot, that the more processors we're adding, we're only obtaining about the same amount of speed up factor. So why is that? That's because our computational grid is only 100 grid points. So when we had a serial run, we had 100 grid points on a single processor. When we had a parallel run with 2 processors, we had 50 grid points on each processor. When we had 4 CPUs, we had 25 grid points on each processor. Why didn't it go down? Well, it's because of communication. As the solver progresses, each CPU must talk to other CPUs. The amount of communication time between CPUs keeps essentially increasing with the number of CPUs that divide the grid. And so the communication time has kept increasing, and it's balancing the speed of each processor analyzing a less number of grid points. So there's a balance of power here. You cannot take a problem of finite size and keep increasing the number of CPUs and expect to get an ideal linear speed up with the number of CPUs increasing. These are part of parallelization studies. A good parallel code, which we might run in my research group, might have excellent communication with very little loss or entropy from communication, up to thousands and thousands of processors. These studies are conducted by almost all CFD groups when they're studying their parallelization of the code, and not only for one problem like SOD SHOC 2 problem, but across a whole range of problems and applications from low-speed flow to high-speed flow. Let's change subjects, and let's look at some flow visualizations. These are from Van Dyke's book on flow visualization, and I would just like to mention what they are so you can start getting a better physical idea of what the flows look like we'll be studying in this class. The first flow is a creeping attached flow. So creeping flows are flows where the fluid moves extremely slowly. Oftentimes, we can get rid of the nonlinear term in the momentum equation and reduce the problem to a Stokes flow, which is linear, of course, and has analytical solutions for select geometry and boundary conditions. There are very few analytical solutions. What you're seeing here in the upper right corner is a cylinder and cross flow with little die lines. The flow moves from left to right, and it just creeps over the cylinder and comes back. It looks to be completely laminar. In the lower right corner, we have a plate and an angle, and once again, the streamlines from these die lines creep around and come back and reattach. It is completely laminar, low-speed flow. Typically, in solvers, there's something called preconditioning, which we need to do and perform, which is like a matrix operation, if you will. And we'll talk about these later in this class. But often we can actually solve these types of problems with potential flow solvers, which are the numerical implementation of the potential flow equations, which you studied, and you found analytical solutions, hopefully, for the cylinder problem, at least in your previous classes. Another flow might be some sort of detached laminar flow. So this might be where we take the same bodies and we just increase the velocity a little bit and the flow detaches. It is no longer attached and it separates from the body. So these are creeping flows that are separating. These occur in nature too. If you've gone down to a stream and you look down in it, and you might see a very slow speed water flow, and maybe you see leaves or little particles in the stream going behind rocks and separating out, and maybe a tiny little bit of swirl in them. It's transitional, but still laminar. You've seen this. If you turn on your faucet a tiny little bit and it's just a steady stream of water, you're seeing the nice laminar flow. In this case, these are the same bodies, but they're just slowly moving around. These are a little bit more complicated because, of course, now we're going away from truly potential flow and we're getting separation and little circulation zones forming. For example, in the lower right figure, we have a cavity flow. Flow moves from left to right. This black part is the wind tunnel wall, and we're seeing through a piece of glass into the cavity. You can see the stream lines or these streak lines from dye or smoke are moving left and right in laminar fashion, but in the cavity along, there's some swirl seen. That's the circulation. There's circulation in the flow in the cavity. These types of flows are also going to use preconditioning techniques, and they're probably incompressible. And you can see these in engineering in some select cases, and of course in nature. The laminar boundary layer is probably one of the most popular flows to study initially. So this is where it could be unsteady and accelerating or deaccelerating, but typically it's stationary flow or time invariant. It's steady flow. And there aren't any turbulent fluctuations. It's not a turbulent flow. So in this particular picture, what we have is something moving from left to right. The flow is moving from left to right, and where my cursor is the wall in the lower part of the figure, and this y-axis here, this line releases something like a dye at a particular time. The flow is already developed and now we're injecting it. And what happens is you're seeing that front of the released material into the flow. And you can see this is, if this was the y-axis and this is the x-axis, that as we move away from the wall, it must mean that the velocity is increasing as some function away from the wall. And this actually happens to fall exactly into a laminar boundary layer velocity profile. This is an amazing result, and it was studied by Ludwig Prandtl, and his student Blasius. And Blasius came up with an analytical solution for this case. So there is an analytical solution for the laminar boundary layer, and it's a wonderful case to study. Mind you, this is for zero pressure gradient. This is an excellent first case for current researchers and students to run and try and see if their CFD solution matches that result. Another case is airfoil separation. This is where we have flow past an airfoil, but now the flow is separating. This could also be a laminar flow. This particular image is from Onera. And we have smoke lines or dye lines in the flow moving from left to right. This black part here is the airfoil. These light part of the image and dark part of the image here is just from my camera and lights casting a shadow in the image. You'll see that some here, and I apologize for that. Anyway, you can see on the bottom part of the airfoil, these lines, the flow comes along and it remains relatively attached to the airfoil and it keeps going. On the pressure side of the airfoil, the lines come along, and some of them just along here are just nice and laminar attached. Oh, but here's a separation region. So a laminar separation or turbulent separation on a airfoil is extremely difficult to predict. Another classical flow is simply a block on the side of a wind tunnel, and they'll put windows on each side of the wind tunnel and put a camera through it and put in dye in the wind tunnel to visualize it. Here, the block is seen and the wind tunnel wall is this dark color because, of course, light can't pass through the wind tunnel wall. And so here's the block. Flow moves left to right. And so here's like where the flow is incoming from the left and it goes to the right. Up near the top of this particular tunnel, there's almost no disturbance. Down near the wall, the flow comes up and it comes up over the top of the block, the leading edge lip of the block. There's some circulation region in here and it flows over the top and it separates, and there's these large turbulent wakes in the flow. So this flow goes from a nice laminar flow up near the top, down through a transitional region and down through a fully turbulent region. This flow is not two-dimensional. A key characteristic of all turbulent flows are that they are three-dimensional. Turbulence in nature must be three dimensions because the vortices must be able to stretch and break down. You cannot have a vortex stretching in two dimensions. It's just not possible. There's a whole mathematical theory and physical verification of these points, which you might see in turbulence books or turbulence books on CFD for applications and prediction. So this is a very, very difficult flow to predict. You can do this in two-dimensional CFD or three-dimensional. And we'll look at these types of flows in this class. Another type of flow which becomes more interesting because it's higher speed. I like high speed flows. I'm an aerospace person by trade. And it becomes compressible. As we increase the Mach number, that is the velocity divided by the speed of sound, then we have compressibility effects, meaning the density fluctuations in the flow. So when you have high speed flows with compressibility effects, you have to use a compressible solver. Here's two examples here in the lower left and the lower right. So what we have is a bullet fired from the right to the left, and a high-speed camera basically takes its picture. All they're doing between these two photos is changing essentially the exposure length. In the left photo, you see the tip of the bullet and the trailing edge of the bullet. If we fix our frame of reference to the bullet, then we might say that the flow moves from left to right instead of being stationary relative to the bullet. This is a high-speed capture of the particular bullet. And what we're seeing here, these black lines are not artifacts, they actually exist, and those are represented by shock waves attached to the bullet, and they're oscillating back and forth as this particular bullet travels. So the flow comes in and it goes to the shock wave, and the pressure and density increase and it moves downstream. Behind the bullet, we see these light and dark oscillations. So you're getting something like a Kármán vortex street. It's not really, but something like that behind the bullet. High degrees of compressibility and all these strangulations, which might look like clouds or mountains from outer space. That's the turbulence. There's turbulence in the wake. So it's a high-speed, compressible, turbulent wake with shocks and expansions. This is an extremely difficult case in computational fluid dynamics to predict, and is a part of the reason this has driven high-performance computing, CFD, and processor development through the Cold War. On the right, we see the exact same image, but which is essentially time average or uses a longer exposure. So you can see here the same trailing shocks in the wake are still captured, but you can't see the oscillating shock waves because they've been smeared out over the exposure of the camera. Can we do these problems with computational fluid dynamics? Yes, we can, but is it extremely difficult? The case on the right, which is the so-called steady case or time average case, is much easier to predict. We'll focus on the RANS-based, the Reynolds average Navier-Stokes equations, to predict equations on the right in the steady framework. To do predictions like to capture a time instantaneous snapshot on the left, we would have to turn to supercomputing. And unfortunately, I think we don't have those kinds of resources to teach a class, of course, for your first time using CFD. Right now, it's much better to focus on the fundamentals and build those up so one day you can try those more complicated cases on the left. And I should also mention that these images weren't just taken with a camera. It's a special camera system with mirrors. So this is called a Schlieren system. What you're seeing are actually gradients, the magnitude of one particular component of the gradient of density, typically in the direction from the top to the bottom of the page. Transitional flows in computational fluid dynamics are extremely difficult to predict. Let's look at one transitional flow here in the figure on the right from Van Dyke. These are simply dye lines in a tube filled with a liquid. So here's essentially the walls of the tube for the first case, and the middle line is the dye line. This is obviously a stable flow. The dye line is not disturbed, it's moving nice and smoothly down the middle of the tube. Now all we do is increase the velocity in the tube slightly and keep everything else the same. And we notice the dye line on either side of the walls of the tube are starting to oscillate some, and they're creating little ripples. The flow is now becoming transitional. That is, mean it's containing instabilities. The flow has become unstable, and it's going away from that nice stable laminar flow. It's transitional. It's going to transition to turbulence, but not yet. It might be oscillating from a laminar flow to a turbulent flow and back and forth at almost unpredictable intervals. If we increase the velocity even more, then we start to get some ripples and breakdown, and increase the velocity even more like in the lower right flow, and we're getting some very strange structures that are breaking down into smaller structures and smaller structures, and this is becoming a turbulent flow, fully turbulent flow. It must be said it's very difficult to predict transitional flows in CFD. The onset of turbulence or transition is extremely difficult to predict. And there's very few CFD codes that are going to be able to do that in a realistic engineering flow. In fact, there's a lot of empiricism in the CFD codes to try and accurately predict transition, and it's a topic of current research in universities and industry and academics. One might ask, how do you trigger the onset of the instability in a CFD code? Some people believe that just the inherent error in the numerics of the solver will cause it to be transitional. Other people try and trip that with some factor or hard-coded parameters in their CFD solver. Some people might say, oh, the transition on airfoil occurs at some specific location before they even start the solver. These are all empirical or ad hoc methods. There are people trying to create codes which predict the location or transitional speeds on their own. You can see these transitional flows from laminar to transitional to turbulent in your kitchen. Go in to your kitchen faucet or any other slow speed water source that you can control, and gently turn it on. You'll notice at first that just a rod of water comes down from the faucet to the basin. This is a laminar flow. If you increase the speed of that flow, you'll see it start to oscillate. This is transitional, so it's going to be oscillating to a turbulent state back to a laminar state. You found the critical value of some non-dimensional parameter for that particular flow, which is transitional. It's becoming unstable. As you increase that velocity of the faucet even more, then you're going to start seeing a lot of chaotic behavior in the stream from your faucet. So go try it. It's something fun to do in the kitchen. You can do at your home. We've now looked at flows from low speed to high speed in external aerodynamics. We've also looked at the transitional cases. But there might be flows that are dominated by, say, convection. These are heat transfer driven problems. So if you've taken and had the fortune to take a heat transfer class, which is typically offered at most universities, then you'll see that in the convection problem might be driven by like a heat transfer or temperature boundary condition. So these flows are driven by a temperature difference. You can also see this in like a kitchen experiment, if you will. So if you can go in and get a small pan with a very small amount of water, and you can vary the heat at the bottom of the pan, that's like changing a temperature boundary condition. You can look down, and if you're lucky, you can try with the right light and see these little convection cells that form. These are their own kind of instabilities that are happening, and these are called the Barnard instabilities. And you can actually see these on the sun. There are actually Barnard convection instabilities on the sun. So it's quite amazing that a lot of the same physics and fluid dynamics, which we can find with CFD, can also be seen on a large scale like the sun, or even a tiny, tiny scale like in the pan of our kitchen. Another very, very difficult part of CFD is predicting the dynamics of turbulent wakes. So if you've shot a golf ball at high speed, it creates a turbulent wake behind it. If you have a submarine underwater, there might be some turbulence in its wake. If you look behind a ship, it has a turbulent wake. If you look at an island and there's water flowing past the island, you can look at that water, there's a turbulent wake. If you look at a vehicle returning to Earth or going to Mars, a capsule re-entering the atmosphere, or the airflow behind the space shuttle, it also has a turbulent wake. So turbulent wakes are found in nature and in engineering. In this image from Van Dyke, you see there's a turbulent wake far behind a projectile. And this is also a type of visualization. Out here in this single gray color, roughly, this is just the ambient air. Behind this projectile, you see a lot of these granulations in the flow. This is also highly, highly turbulent flow. It's high Reynolds number. And each of these little things, granulations, represent turbulent structures at all kinds of different scales. This is very, very difficult to model or resolve in computational fluid dynamics. We will look at some of these types of wake flows in this class of CFD, and we're going to try and model them statistically, because often we can predict the statistics of turbulence, but not necessarily the exact dynamics. Now, in this flow is also complicated because there's regions of laminar flow, like out here in the single color, and regions of turbulent and transitional flows in the interior and edges, respectively. This can also be compressible. It could be high speed or very low speed. And you'll have to know something about the physics of the flow and what's happening so you can set the parameters of your computational fluid dynamics solver correctly. One of my personal favorite examples is grid turbulence. If you look at this lower figure by Van Dyke, we can see how grid generation is developed. Grid turbulence is developed. We have a laminar flow coming from left to right initially, and there's a grid. This might be just a honeycomb structure with some porosity, or a screen like you have on a porch. And the flow goes through the screen or honeycomb structure, and it reduces the size. So see, here are some pores, and here's a blockage. Here are some pores, and here's a blockage. Here's some pores and a blockage. And the flow goes to the pores, and it comes out. And about 8 to 10 grid diameters downstream, the flow seems to do something very strange and almost unpredictable. It transitions. It transitions from the laminar flow into a transitional flow and then fully turbulent flow. If I put my hot wires here to measure velocity, for example, I'll see that the statistics of this turbulence are homogeneous and isotropic. Homogeneous meaning that they're not changing with space, and isotropic meaning the statistics do not change with rotation at any point. That is a fascinating property. You'll see these types of systems put in wind tunnels before the test section. The purpose of the grids is to remove the turbulence. but you can see in this case, it's induced turbulence. So this is something very strange that you can think about. Why do grids create turbulence, but they're put in wind tunnels? Think about that. So the difficulty of these problems is how to predict the onset and levels of turbulence from a grid, and to make sure that the turbulence you don't want in your wind tunnel is removed. These things can be done with theory and CFD typically, and often in experiment too. The key to these problems is calculating the dissipation rate of turbulence accurately, and the rest of the problem can be solved analytically often, if you know the properties of the grid. This is often studied in CFD, but is an extremely, extremely difficult problem to solve. In fact, it almost needs an unstudied solver which is able to predict these transitional properties. Let's look again at the free surfaces and wakes. So here in the upper right, you see a ship, and you see a turbulent wake behind it. This is simply taken from an overhead view of the ocean surface. So you can, if you've been on a ship, you can see these types of wakes when you stand on the back and look out the back. We can also look at these types of surface flows from the side. So here in this case, we have little bubbles, and we have the surface and ripples. So predicting surface waves and turbulent wakes from ships or in free surface flows is extremely difficult, because now you have what we call in computational fluid dynamics a multi-phase flow, that there's different phases and perhaps even fluids. There's gases and liquids, maybe plasmas, there could be bubble dynamics, and we have to track the surface of the wake waves in a simpler problem that's laminar down here, like in the lower figure or the upper figure. There's also computational fluid dynamics solvers that look strictly at something like wave calculations of the ocean or harbors. This is another type of computational fluid dynamics, which is perhaps underappreciated in the aerospace field. These all apply to submarines too. So you can imagine that cavitation from a submarine propeller creates a lot of noise. It also damages propellers and ships. So in the shipping industry, the defense industry, for naval vessels, you might try and reduce noise and cavitation from the propeller system so that they're not detected by sonar. This is also an interesting area of CFD, which many students are unaware and don't consider. We've looked at high-speed flow, low-speed flow, creeping flow, subsonic flow. Let's look at a transonic flow. This image shows one particular model moving at Mach 1.1. That's 1.1 times the ambient speed of sound, and it's moving from right to left. This black part is the aerodynamic body with fins. You can see in this image, the Schlieren image, that as the flow moves from left to right, there's these lines that form around it, and they're almost normal to the flow. That is, the face of these waves, which are these dark lines, are normal to the flow. Those are shock waves, and they're very close to normal shock waves, meaning that they're perpendicular to the flow direction. And they're located near Mach 1.1. Transonic CFD, transonic wind tunnel testing, is one of the most difficult areas of aerospace engineering, especially in the fluid dynamics community. It is very difficult to predict the positions of these waves with CFD. You can also see in this image, which I forgot to mention, that there's a turbulent wake and boundary layer, which you can actually see around the vehicle here. You can see these granulations in the Schlieren image. It's quite beautiful. You can also see here that in some cases there's different types of waves, and they're barely noticeable, but those are called the Prandtl-Meyer expansion waves, discovered and named after Ludwig Prandtl and his student Theodor Meyer. We talk about these two people a lot in my compressible flow class. Now, you might ask yourself, why are these oblique shock waves or normal shock waves near the end of the vehicle here? Why do they have larger angles than the ones near the front? So remember, the shock wave angle is shallower relative to the flow direction if it is a stronger shock, meaning the flow velocity in front of this shock wave, it's much stronger than the flow velocity of this shock wave. Why is that? That's something that's a little bit peculiar with transonic flow, and I would like you to think about. Let's now consider the cylinder and cross-flow problem. This is another high-speed problem. This is a supersonic flow. In the lower left, we have the Schlieren of the flow moving from left to right, and there's a strong bow shock that forms in front of it. This flow is very much like the re-entry aerodynamics in a flow that you would see in a capsule returning to Earth from space. So there's the bow shock, and the flow comes along and it goes through the bow shock and reaccelerates around the body, and then there's another shock wave found at this location. It comes back and it separates after the shock, and there's a turbulent wake behind the cylinder. There's also these strange waves coming out of the turbulent wake. What are those? On the right, you can see a different kind of image of visualization. This is a shadow graph. So what happens in the wind tunnels, they have the cylinder looking in the cross-stream direction, the spanways direction down the cylinder, and you have these so-called zebra striping. When the wind tunnel's off and the camera's on, you do not see any of this strange strangulation. Comparing these two figures, you have one with this shock from the Schlieren, and you have the same bow shock from the zebra stripe shadow graph. It's a very, very high speed flow. Now, in these regions, you can see that the zebra stripes are just at a little bit different position than the original picture, likely, but they're all relative to each other. Before the shock, they're all just like you would see with the wind tunnel off. So in a supersonic flow, all this airflow here knows nothing about what's going to happen downstream. It's supersonic. Now, when the shock happens, they're all bent and twisted. That's because the shock wave contains large density gradients. When light goes through a density gradient in the air, to the camera in this case, it is bent or refracted by the density gradients. It is a fascinating subject. If I sent a laser through this particular shock wave, it would also be bent. So what you're seeing is the bending of all these zebra striping from the background as it comes to the camera. It allows us, in an experimental technique, to exactly see the striping of the wave. Unfortunately, no computational fluid dynamics code for a long time could predict this type of case. And we are particularly interested in the distance from the leading edge of the body to the front of the shock wave. That is the standoff distance of the shock. In the 1980s, this was a topic of a lot of research, and nobody could have a CFD code that could easily do this robustly. They would all fail or diverge. Today, this problem can easily be solved if you're careful with our contemporary CFD codes, and we will be looking at these types of problems in this class. It's amazing that today we can find these on a little laptop like we use in this class. That's our personal machine, and in the 1980s we had to use supercomputers and couldn't find these types of solutions with CFD. One of my favorite problems to study is the Supersonic Jet. Let's look at this picture from Van Dyke. Here's a nozzle, and the airflow comes in through the nozzle, and for the Schlieren image, which is a picture of the density gradients, and it emerges supersonically as a turbulent jet. This is exactly like the turbulent jets you would see from a rocket launch or behind a high-performance jet engine. This is all fully turbulent flow, and it contains shock waves in the plume. We'll look at more of those images later. These are waves coming out. You can see these little waves here and here. What are those waves? Those are actually Mach waves, and they're acoustic waves. They're extremely loud, and they can damage a launch pad structure or vibrate a fighter aircraft over time and lead to failure. This problem is wonderful to study if you're in computational fluid dynamics, and it contains almost every type of problem in a single experiment or simulation that you could possibly care about in CFD, I think. It contains standing, subsonic, transonic, and supersonic flows. So the flow field in this problem is very, very, very slow and creeping. It's subsonic, it's transonic, meaning it's near Mach 1. It's supersonic above Mach 1. Very difficult flow. It contains regions which are completely laminar, that are acoustic regions, and fully turbulent regions. So a single CFD solver to solve this problem has to handle all these types of flows at once. It has to capture the transitional effects of the turbulence within the nozzle from laminar to turbulent, and outside the nozzle in some cases. It has to handle shock waves, not only in the laminar regime, but also in the turbulent regime. And capturing and resolving shock waves in a turbulent flow in CFD is extremely difficult, and there's a whole field called shock capturing methods which takes care of this. There's also expansion waves in the plume that has to be taken account for. So you can imagine the task of creating this flow field and trying to match experimental results, which would be extremely difficult. You can see a Schlieren video of these types of flows at this link here. Let's turn our attention to a different subject of natural visualization and natural visualizations compared to CFD. We might do this by looking at clouds or vapor, if you will, forming around vehicles as they fly through the sky. This particular equation is for the relative humidity of vaporization, if you will go as the relative humidity in the undisturbed atmosphere times the fraction of the pressure at some particular point around the vehicle divided by the ambient pressure times 10 to this power of temperatures at a particular point divided by the ambient temperature. This is a simple empirical formula, for example, where if this relative humidity is a critical value, then the humidity in the air will condense and become little tiny water droplets. This is what you see when a particular pressure and temperature drops below certain points. This is illustrated in the airfoil example. You see on the lower left here where the air moves from left to right, and there's some expansion and compression of the flow, and the flow becomes visible because little water droplets are coming out of the water. This happens in wind tunnels too. If you have a Mach 5 or Mach 6 wind tunnel and you accelerate the air from 0 to say Mach 5 or 6, then you'll have actually a river of water coming out of your wind tunnel because all that water is coming from the air because your pressure and temperatures have dropped to a value while the air condenses. You can see a figure of this process in the lower right corner where the y-axis is temperature and the x-axis is along the distance of the particular wind tunnel nozzle. So initially, the stream temperature is going to be lowered towards the dew point in a particular portion of that nozzle, and then you'll have water in your wind tunnel. The way in practice people get rid of this in wind tunnels, of course, is to have a dehumidifying system, which is extremely complex because if you're moving a lot of air at high speed through your wind tunnel, you have to remove all that water from the air beforehand. On my YouTube channel, I posted some videos of these types of things. Here's another picture of the process. On the y-axis, we have static pressure. On the x-axis, we have static temperature. And we have the liquid and vapor phase. Along this line is where that relative humidity is 1 from the previous equation. If you can see RH is less than 1, then of course the condensation ends, and RH is greater than 1, the condensation begins. So this is a simple way of looking at the static pressures and static temperatures at a particular point around the vehicle and seeing if there's going to be some condensation or vaporization of the water in the air. Let's look at this through practice and visualizations. This visualization is the so-called gull pattern and wingtip vertices above two particular aircraft. The upper one is from a picture in Mach 0.82, and then the lower one is one for a Boeing 747, the humidity, the relative humidity calculation. Look at the upper left wing of the upper aircraft at Mach 0.82. You'll see this sort of like dome-shaped vapor on top of the aircraft. Here's another example. On the right, we have the CFD of a simple airfoil. On the left, we have the parental Gallard cone forming around what I believe is an F-14. You can see there's some angle of this cone, and this general angle matches the airfoil case. This is where condensation is happening because the static pressures and temperatures of the flow have become small enough for condensation to form. So it's very interesting that we can do relative humidity calculations with computational fluid dynamics and compare them directly with calculations of the vehicles in the atmosphere and take a photograph and put it side by side with the CFD. That's super cool and actually quite aesthetic. A fun part of CFD. Here's the Concorde taking off. So if you look at the Concorde, it generally creates lift by these vortices that form on the leading edge of the delta wing, and they form and grow down the top, and they become bigger and bigger and shut off the aircraft. Here's the same type of calculation where they've included the relative humidity calculation for a delta wing. You can see even without a fuselage on the wing, these vortices form and they grow downstream and remain sort of attached to the leading edge on each side. So what you're seeing is the relative humidity calculations on top of a delta wing in CFD compared directly with the photo, and you can see these same vortices, and relative humidity forming on the upper side of the Concorde. It's beautiful. Here's another simple case looking at streamlined vorticities from the leading edge of a Boeing 737 during climb. So in the picture, you can see these streamlined vorticities. This is it. In the middle of vorticity is very, very low pressures, and that pressure goes below the relative humidity critical point, and you can see these same streamlines plotted along here. So we can visualize these for the same case roughly. We can see these same streamlines coming down and curling around each other into like a vortex, just like you see on the streamlines of a Boeing 737. If you've gone to an air show, you might have seen an F-16 pulling some maneuvers. Maybe this is an F-16 pulling up on the stick, making a maneuver. And you can see these same types of vorticities coming along and forming along where the root of the wing is to the fuselage and coming off the aircraft. You can see the same type of flow by plotting streamlines of a corresponding F-16 making the same maneuver. So these are full body CFD calculations to find aerodynamics in different maneuvers. And it's really cool that we can use natural visualization of a flow field to try and help validate our solvers. I would not trust a validation only on natural visualization. I would personally want some wind tunnel data at the very least, if not flight test data with pressure reports and other types of measurements on the aircraft. Let's look at another example. Here's an F-18 looking from the wingtip down towards the fuselage, and you'll see these same relative humidity coming and forming along these vortices, coming up and shedding and streaming off the top of the aircraft. We can see the same thing in the CFD calculation when the vortices are coming along. Might also look at transonic aerodynamics. As I said before, transonic aerodynamics is one of the most complicated types of flows to predict. Here's a particular Schlern of a space shuttle type configuration. There's different shock waves forming on it. And here's two fighter aircraft where you're getting these types of little disk clouds, which are forming near the transonic shocks. They're very like Prandtl Glovert waves. You can do this both experimentally and computationally. It's very difficult in both cases. Why? Well, we'll talk about the mathematical details of this later, but generally the eigenvalues of our problem, some of them are very close to zero, and these eigenvalues basically dictate the speed at which information travels through the spatial domain, and they're almost standing. This makes it a very computationally difficult problem to solve, because it's not a well-posed problem. In wind tunnels, you have essentially the same problem, that you're getting standing shocks, and these standing shocks build up in a wind tunnel and completely ruin your measurements. We'll talk about that kind of wind tunnel testing briefly in the class if we have time. You can also look at the wingtips of the space shuttle. So here's a space shuttle, and along these wingtips, there's wingtip vortices. And of course, the pressures and static temperatures inside these vortices become very low, and the water in the air condenses. You can also see it very faintly in this particular picture. Both of these, of course, are pictures from NASA originally. More flow visualizations, and there has been CFD done of the space shuttle showing these. There's many other types of CFD that's found its way in other industries. I just wanted to put another one so we can have a little bit of diversity in the topics of the class. This one is one of my favorites, as I mentioned before, flow through the human heart. So you can see sort of a image of an actual human heart with superimposed solutions of computational fluid dynamics. A lot of this technology has come from the aerospace industry and made its way to other industries. For example, the biofluid mechanics field is a huge user of all the CFD technology. And of course, there's extra and new technology and mathematics emerging to do biomechanical flows, which have all kinds of different issues than a typical traditional aerospace flow. For example, there might be soft tissues. The blood is non-Newtonian. Those are two major things today. It's hard to imagine where a flow has occurred that CFD approaches have not been applied. We've looked at many of these visualizations, and they're very interesting. We can even show how natural visualizations we've seen with our eyes correspond to computational fluid dynamic flows. These are not rigorous validations, but they help explain what we see in nature. We've also looked at all these fundamental physical flows, which we'll be studying in this class. Remember, if you cannot do a CFD prediction of a basic flow, there's no hope of doing it for an entire aircraft engine or aircraft, or even more complicated problems out there. It is always important to choose the correct CFD solver for the problem. If you choose the wrong solver for the problem, it is impossible to get a solution that's physically meaningful. There's a lot of commercial codes, and we used to use these commercial codes in this class, and we've turned to open source codes. It is easy to learn any of these types of codes if you used one. So don't be so concerned about which code you're learning first. If you can learn, say, star CCM, it's easy to learn Fluent. If you can learn the codes and suites in our class, where you'll be able to see the source code if you so desire, you can even more easily pick up Fluent or star CCM or any other commercial or other research type of CFD solver. I do believe this is the first approach. And I've worked with a lot of people in CFD, and I do believe that the people who looked at source code and learned individual modules and built up to more complicated CFD packages are the best users. Next time, we're going to be looking at a mathematical survey that is important for CFD analysis. We'll look at some tensor analysis and linear algebra, hopefully as a review. And if you don't know anything about linear algebra or tensor analysis, now is a good time to go find something online or a book in your local library to understand it. The next thing we'll do, which is extremely important, is the classifications of second-order partial differential equations. These will help explain to you why transonic flows and hypersonic flows and creeping flows are so difficult to predict with CFD or even do experiments on. Then we'll look at two of the most important partial differential equations, the wave equation and the diffusion equation. We'll summarize the last class in our introductory module by looking at the Navier-Stokes problem. Thank you very much for your time today. I'm your professor, Steve Miller.